So surface area. So remember, surface area is of an object like a box, for example. All you do is find the area of each side of the box. So that same concept is applied to surfaces in three dimensions. So given a surface of the equation z equals f of xy, where f is a continuous function, or yeah, you could in terms of x and y. So what we're going to do is pretty much do exactly what we do like normally. We would break up the entire surface into small rectangles, find the area of each individual rectangle, and then sum them up. And that's pretty much what three-dimensional surface area is about. Is the only difference is because we're doing in two dimensions, x respect to x and respect to y, this delta t is the change in the area of that rectangle over the period of x and y. Okay? So a fundamental fact, which we'll go into much more detail in later concepts, is given this surface, we kind of already know how to do this kind of stuff using in vector format. Now, we're not going to go into full-on vector format. This is a little bit more precursor of what's going to happen later on in the course, or later on you'll be learning, is if I convert this into vector format, and I just convert this little box there into vector formats here, I now have two vectors, A and B, coming from this point there. Now, if I get their cross product, this gives me the area of the parallelogram that vectors A and B create. Now, that's going on farther. I know it's not this concept here. However, this will come into play far more detail later on, is how do you find the full-on surface area, or called surface integral, later on in the course, where you get the cross product of. But for now, we're just going to simply do an estimation of it. And it's about the same thing as you guys would do in single variable calculus. So the area of the surface is of the equation z equals f of xy, where fx and fy are the partial derivatives with respect to x and y respectively, gives us this. Okay. Now, in most cases, this is pretty bad. And I will usually have it dt, so I'll usually do dy dx. The square root is what gets a lot of people in trouble. And most of the time, polar coordinates is the way to go when it comes to these kind of concepts. Okay. So for example, find the surface area of the, of the surface z equals x squared plus 2y that lies above the triangle region T in the xy plane with vertices 0, 0, 1, 0, and 1, 1. So first off, let's see what's going on. What is our surface D we're dealing with? Okay. So our point is 0, 0, 1, 0, and 1, 1. So here's our region D. Okay. All right, so we're going to find the surface area over this region and above the surface, so just this part of it itself. Okay, so according to our process, we need to find the double integral from x to y. So x goes from 0 to 1, and y goes from 0 to this line here. Okay. Well, this is just the line y equals x, because if it's, or you could put y equals x plus 0, because the y-intercept is 0. So we know y has to go from 0 to x. Okay. And now we plug everything in, so we're going to get the double integral, and we're going to go from x last, so from 0 to 1, and then y 0 to x of this portion here. So therefore, if I take the partial derivative with respect to x here, that gives me 2x. And I take the partial derivative with respect to y, that just gives me 2. I'm going to go dy dx. Simplifying this a little bit more, we get that. Okay. Now this isn't bad, because we take the integral with respect to y is just itself, value it at x and 0. Well, that's kind of nice because this just ends up being itself with just the x in the front. And 0 cancels out, so it's minus 0. So literally it just gives us that, which is nice. And now we're going to u substitution on the inside. So divide by 4, and we get our u sub. There and there. So this ends up being the integral of u to the 1/2 du, which ends up being u to the 3/2 with a 2 and a 3 there, times the 1/4 in the front. Oh, what am I saying? This is 4. This is an 8. 2 times 4 is 8, so this is 1/8. 1/8 and an 1/8. There we go. All right, so now going backwards and plugging in what u was to begin with, these cancel get you 1/12, and this ends up being u, so 4x squared plus 5 raised to the 3/2 evaluated at 0 and 1. So if we do this individually, I'm just going to put the 1/12 on the outside. So plug in 1, that's 4, that's 9. So 9 to the 3/2 minus, if I plug in 0, it's just 5 to the 3/2. So plugging this in a calculator, you get approximately 1.32. All right, so like I said earlier, the square root is what gets a lot of people, and it gets trickier. So whenever you deal with square roots, most of the time, not going to say everything, but most of the time you could even have done it here. A lot of times polar coordinates is the way to go. So as is going to happen in this example. So find the surface area of the surface z equals x squared plus y squared that lies under the plane z equals 9. Now, in most cases I would give you the graph already done in 3 dimensions, but this one's actually not that bad to do. So this is the plane, for example, z equals 9. And our surface looks like this. In 3 dimensions, this goes all the way around, and we are plane like right slashes the whole plane there. So this is z is equal to x squared plus y squared. Okay. All right, so I'm not going to find the bounds of x and y just yet. I'm just going to put the double integral for now so you can see how this would work out. So we're taking the double integral of this respect to the partial derivative with respect to x, so that's just 2x, and if I square it, that gives me 4x squared. And same thing here, partial with respect to y, that gives me 2y, and if I square it, that also gives me 4y squared plus 1. dy dx. Okay. Now, at this point, I'm going to go into polar coordinates. Okay. So, quick reminder. Polar coordinates looks like that. So, which makes this a lot more easy to deal with because now this ends up being, cosine squared plus sine squared equals 1. So this is 4r squared plus 1 on the inside, which makes it much easier to deal with accordingly. However, we need to find our bounds, okay, about our integrations. So remember, we're comparing to the polar, therefore it's theta and r, what we're dealing with. Now, theta is pretty straightforward. Well, let's just go with r first. So if I project this all completely down, I get a circle down here, right? Just project the top down. Okay, so this circle ends up being a radius of what? 3. So R can go from 0 radius, which is the exact center here, all the way up to 3. And that's easy to write. You just plug in 1 here, and just put everything in polar coordinates. You could do solve for Z as well. So it goes from 0 to 3. And theta goes all the way around. So theta goes completely around the entire portion. So it goes from 0 to 2 pi. So now our integral goes from 0 to 2 pi and then 0 to 3 of this. So r times all this going to be 4r squared plus 1 dr d theta. And now notice now becomes exactly like we just about to do as above. It's the exact same template. And that's what polar coordinates helps us do. So using the same process, so this ends up being the integral, or 1/8 the integral of u to the 1/2 power. So notice the exact same. So u to the 3/2 and then 2/3 down here. So just quickly skip that step. And essentially, I plug in 0 and 3 back into here. So 3 squared is 9 times 4 is 36 plus 1 is 37. So 37 to the 3/2 power minus plug in 0. It just gives me 1. And 1 to any power is just 1. And we're going to take the integral of this from 0 to 2 pi d theta. Okay. And that's just itself, right? So there's nothing with respect to theta, so it's just going to be a theta in the front times the subtraction. Okay. So plugging this in the calculator and then subtracting from 1, I get 224.1, and then dividing by 12 essentially, or at 2 theta. So plug in 2 theta, I get roughly this. And there we go. So that's surface area in a nutshell. It's pretty painful. As long as you convert everything polar, the integration isn't as bad sometimes.